So as I was saying, this work I did it during the first year of my PhD is the Hyper Suprime-Cam extended point spreading function, and I work in collaboration with Aaron Robotham, Sabine Belsted, Luke Davis, and Cristina Martinez Lombilla. So a bit of motivation. During my PhD, I measured the intracluster light with HSC SSP PDR3. This is the last public data release, and the intracluster light is a very faint and diffuse stellar component that surrounds clusters and group of galaxies. And we are interested in the intracluster light because it can provide us with an extra tool to analyze how was the assembly history of the system. So why this is important? Because, as I was saying, it has a very low surface brightness nature, and the PSF can, with the scatter light, can affect our intracluster light measurements. So, bit of introduction. We know that the inner part of the PSS is reproduced by the atmospheric turbulence of the place of observation, and we know that the outer PSF is caused by the scatter effects within the telescope and the instruments. And there are several works that have demonstrated that the integrated flux in this extended width can be significant. So getting rid of this faint light from bright sources at large distances can be useful if we want to measure a LSB filter with more precision. And we have reconstructed HSC-SSP PDR3 PSS following this method, the one presented in Infante Science et al. 2020, which was originally developed to construct the SDSS PSFs. Here I show you briefly the 2D images of these PSFs with an extension of around 8 arc-minutes. So this method consists of selecting stars of different magnitude ranges to reconstruct the different parts of the PSS. This is, we select very bright stars for the outer part, which they can give information at far distance from the center, but we know they are highly saturated in the center, as you can see in the blue profile, which is the median stack of all of the stars. So the idea is that we use more fainter stars to reconstruct the inner parts. We did that. We follow this method. We slightly changed the magnitude ranges, and we also added one part because it was more convenient for our work. And here I show you the stack of all the bright stars with magnitude less than 8, and the flux distribution of this profile, where you can see that it's extended, but in the middle is saturated. So we avoid all of these pixels and we go to the next stack. We literally replace all of these pixels inside a radius of 150. And this is a combination of both stacks, the outer and the middle one. Same idea, the center is saturated and we replace with the next stack. And the final step is inside this very tiny circle of 20 radius, we use the core stack. So this gives us a PSF that is completely smooth and is not saturated in the center and extended in the wings. So here with this plot, what I show is the profiles that I was showing before. And on the right, we see how the different stacks contribute to the different parts of the PSF. And in addition, in pale blue, I have highlighted the flux error per pixel associated with each of the 4 median stacks. So here, what I show you is the flux distribution of the 5 PSFs, the 5 bands of HC, GR, I, ZY, where you can see that these peaks or spikes in the Y band are only present in this band, and this is due to some internal reflections on the CCD of that impact on the only long wavelengths. Some data about these PSFs is that the full width half maximum is around 0.7 seconds. The extension is around 5 arc-minutes. And to give you an idea of the power of these PSFs, the difference in in magnitude between the peak and the minimum is around 20 magnitude, which will give you, we would be able to measure a surface brightness value of 28 magnitude per square seconds if we observe a very bright star of magnitude 8 at a distance of 1000 pixels. So this is important for us because it means that we could be able to remove all of this light that can contaminate LSB features. Here are two-dimensional images of all of these 5 PSFs, where I've also highlighted the artifacts that are named like this in the HSC pediatric paper. And what I wanted to highlight here is this vertical feature that is only present in the Y band, called also channel stop. And these are the spikes that I was talking before in the Y band. So all of this work was published in a paper a few months ago. And the good thing also is that we made public the PSF as FITS files in a GitHub repository, where here is the QR code in case anyone is interested. And we also made public the codes to reconstruct the PSF. And due to the similarities in the wide field of view between HSC and SST, the pipeline processing and the depth, this method could be also applicable to reconstruct the LSST PSFs. Here I show a comparison between our HSC PDF3 R-band PSF in blue versus the PSF from two of the most sophisticated telescope for LSB stuff, which are the Bartlett-Smith in green and the Dragonfly in pink. The two pink PSFs are because they use different technique to measure it. And what I wanted to highlight here is that the behavior of our PSF is reasonable, comparable to the other two PSFs, which we already know that these are quite well behaved, or they don't have, they don't scatter so much flags at long distances from the center. So finally, I wanted to show an application of these PSFs where we model a real star image and subtract it from the image. So in the first row, we have the same star across the 5 different bands. In the second row, we have masked all the background sources, and we have also masked the center because it's saturated, and we don't want the fitting code to confuse these fake measurements. And in the third row, I am showing the models of the stars where we have used a two-dimensional fitting code that offers a profile to model, and we have selected the point source profile, convolved it with our PSM model, and renormalized to match the magnitude of the star in the image. So these are the models. They look like the PSFs. The fourth row is the mask image minus the model, so they are the residuals, where we can see some expected residuals around the core of the image. But when we divided this by the image itself, these residuals are kind of smooth around the core of the image. And finally, in the final row, I am showing the same as before, the residuals, but in the same color scale that I used in the first row. This is just for reference. And here, what I'm showing is the flux radial distribution of the first of their star, which is the first row in pale blue, then the mask star, which is the second row in dark blue, where we can see that because we have masked all the background sources, the noise is small, and our model, which is called profit model because the two-dimensional fitting code that I'm using is called profit. I am showing this distribution of the model, where we can see how this is matched well, and also the noise is highly reduced, because as a consequence of the PSF stacking technique. So quick summary of my talk. I reconstructed the extended model of HSC PDR3 PSFs with an extension of around R minutes using Infante-Sainz et al. 2020 method, and this consisted in using stars of different magnitude to reconstruct the different parts of the PSF. We tested the PSF on several applications. The one that I show you today is to say model and subtract a bright star image. And we made public the PSF as FITS files and the reconstruction code on our repository in GitHub. And this method could be also used to derive LSST PSFs. That's all. Thank you.
Can I just speak to you? Does your PSF model depends on the position on the focal plane? And if that depends on that, would that affect the wings in your model, like the outside of the model?
And yes, and my PSF doesn't take into account the field of view of each CCD, so it's a general PSF. So yeah, it's a general model.
Thank you.
Sorry, I was going to say the same thing.
Yeah, so Lucia's work is absolutely beautiful and a really kind of nice way of putting the PSF together for Suprime-Cam. We've been doing some work with a postdoc of mine, Amir Bazkiai, has been working with Rubin DM on a model that in the LSST stack that takes the Suprime-Cam data and does this kind of extended PSF fitting, not over 3 magnitude bands over kind of a single range of stars. But in that we have allowed for variation across the field of view. And there are significant differences in the wings across Suprime-Cam, which has obviously fewer CCDs. I put a link to an early conference paper of his in the Slack so that people could see some of that work. Yeah, there are definitely wing differences across Suprime-Cam.
Yeah, they're very significant because they're coming from the ghost. Most of that wing structure is the ghost and they're a strong functional position. It's true in Sloan as well. Those models you had for the Sloan PSF depend on how close the star is to the edge of the CCD, because that structure is coming in off the inside of the filter. So I think you do have to worry for all these cameras on the spatial structure of the PSF wings. Sorry, the wings of the PSF. It's not from the atmosphere, it's from the cameras.
In the field of view that you can do that spatial modeling? Yes.
We're doing that, yeah.
Oh, yeah.
I could probably give you a number, but I think I just binned the file that had the number in, but it was, no, I can't, sorry. I'll put it in the Slack.
Okay. Have any questions on Slack? Oh, oh yeah, Josh.
Yeah, just a similar question. Do you see any variation in the wings with the seeing in the core? You know, if it's 1 arc second or half arc second, does that matter in the wings?
You mean if we observe different parts of the, if we take spars from different parts, or?
No, I mean if the full width half max seeing is really good versus really bad, does that change the wings at all?
I think it doesn't have an impact of the wings.
You can model it all with the same.
Yeah.
Okay.
Yeah.
Thanks.
If there aren't any more questions, then I'll maybe thank Lucia again. And move on to the next talk. So feel free to interrupt, and we want to make this part very discussion-based and collaborative. So we're looking for input, and we're at the very beginning of this project. So
Hi, I'm Ken Chang, like you, like framework research scientist, and Hébert and I have been working on producing a requirement on the PSF modeling for Rubin based on cosmology. So today I will present these slides on how we produce the preliminary PSF requirements based on cosmic shear. Hopefully this will be extended to other science probes for the part that sets the budget. But this also provides a general way of converting the science requirement to a more technical requirement on PSF modeling. So just to give a bit of context, today I will talk about mostly cosmic shear. So cosmic shear uses the correlation of galaxy shapes to measure recleansing signal. And it's have been one of the science driver of big surveys over the past decades and into the future. It's really important for cosmic shear to measure precisely, which means unbiased amplitude of the recleansing correlation function, so that we can make an inference on one of the cosmology parameter called SA, which is the strength of clustering of matter in the universe. And since the measurement from weak cleansing is currently in potential tension with CMB, understanding the systematics around correlation function of galaxy shape is really important to the overall success of cosmology from Rubin. And in order to measure weak cleansing, we measure the shape of the galaxy. And the shape we see in our image for any galaxy is not the actual shape that the galaxy has, because for any image we measure, including Rubin, the galaxy image is convolved with a PSF that has components from atmosphere, from optics, and from the instrument. And we get sort of a convoluted image that is then pixelized with our detector. So to precisely measure the shape of the galaxy, we need to model the PSF correctly, and especially because PSF model residual is normally correlated, which means in one field or at a certain location on the field, the residual are oriented in the same direction. And that causes a fake cosmic shear-like signal in your galaxy shape. So that's why it's particularly interesting to understand the correlation in PSF modeling correlation. So, before I go through how we set the requirement, I sort of want to go through understanding the PSF systematic in galaxy shape measurement. What that means is there are different sources of PSF modeling error that can cause an error in your galaxy shape. So the first term, I'm trying to use these ellipses for you to understand how PSF modeling error ends up in galaxy shape. So say you start from a true galaxy shape, a round galaxy with elliptical PSF. And the image you will observe is the convolution of the two, which means that your overall image is going to be have an ellipticity because of the PSF, and you are trying to reverse inferring the true galaxy shape from this and the PSF model. And say now your PSF model is wrong in the shape, in that true PSF is clearly an ellipse and you're given a round PSF. If you use that PSF model to measure the galaxy shape, the shape measurement method is going to tell you, oh, the galaxy is probably an elliptical galaxy. But now you see why there is a galaxy shape error if you give it the wrong PSF model. And we call that the modeling error in PSF shape. So similarly, an error in PSF size can also cause an error in your galaxy shape measurement. So this is a little bit more complicated. So similarly, if your shape measurement is given a PSF model with the correct shape, but with a wrong size, in this extreme example, if the PSF is super tiny, then the shape measurement methods are going to think, well, if the PSF is super tiny, then the convolution doesn't change the image overall. So we'll just give you the same, the galaxy measurement will be the same as measurement on the image. And you will still end up with a shape error for the galaxy. So the final type of galaxy shape error I want to talk about is called the leakage. So leakage is not technically a fault of the PSF modeling, rather it's a fault of most shear measurement methods or shape measurement methods have some kind of leakage. What that means is if you give the shape measurement an elliptical PSF, it's not deconvolving that PSF perfectly, so that your final galaxy measurement will have some residual of that PSF shape that is proportional to a tiny factor of alpha. So this alpha is usually really tiny, but for cosmology, it is important to understand that this term would exist for your shape measurement. So in the next few slides, I will go through these baby steps of how we are normally converting our science requirement into a PSF modeling requirement. And we recognize that there are different choices can be made. So I really want to open up to discussion in these, when we discuss these steps and what we really should do for Rubin. Most of our practices are based on previous surveys such as DES or HSC. But what's done in the previous survey might not apply to LSST because we will have less statistical budget. So that means we might want to take different approach from previous surveys. Okay, so baby step one would be obtain the budget for the PSF systematics for overall. So what that means is we should think about how much budget overall does cosmic shear have, or does the 3x2 point has. I listed 3 approaches. So what's normally done in the previous survey is the slightly less ideal approach, which takes a fraction of the covariance matrix, which is the statistical uncertainty for your measurement, and say, oh, my systematic should probably not exceed 0.5%, 0.5 or 50% of my statistical uncertainty. And that's a fair way to do it. The most ideal way to do it, in my mind, is that we should have an envelope of PSF systematic, and make sure that if the PSF systematic is within that envelope, it won't cause a cosmological shift over 0.3 sigma. So that requires some sort of Fisher forecasting, and it's currently not done. But this is, I think, I don't know whether you agree. It's a pretty interesting standalone project to discover sort of in the systematic space, what is the space that wouldn't cause a significant cosmology shift. Why I say that is because you can imagine having 2 bias canceling each other out when you do cosmology, and that's probably allowed because if it doesn't cause an overall issue, it's fine. However, like if some kinds of combination of bias will cause a significant shift in cosmology, then that's not allowed. And there is a what are you doing approach, which is the simplest way of setting your budget is basically multiplying a fraction of the fiducial cosmology data vector. And of course, we're currently taking that approach. You're probably thinking what you're doing. That's how it gets its name. So what I'm showing here is a fiducial cosmic shear signal for LSST without binning, so just one bin and side plus. And we're currently taking the budget to be 1% of that fiducial cosmology. And from the science requirement document, the overall additive bias is allocated 20% from the total budget. So currently we are allocating 20% of the overall budget to PSF additive bias. And I guess a question that I want to bring up is whether that's okay, because I'm not sure if there's other additive bias that's taking that. Oh, I see.
Yeah, go ahead.
Yeah, I can just give some perspective from DES. So in DES, the PSF didn't contribute very much additive. Like we were more worried about the multiplicative stuff with the sizes. So, you know, there were other things that were potentially causing additive things that we were worried about. But in general, the additive shear biases were pretty small in the overall budget. So most of the time, like this is all easier to do once you have data than to do forecasts, because you can just see what you actually have and then propagate that through to see what it does to sigma 8 or omega matter or whatever. And the PSF stuff for us was always negligible compared to the other modeling problems that we had from the theory side. So I don't know if that answered any of the questions, but
Yeah, that makes sense. Yeah, so I think one important thing to mention here is that currently we don't have our shear catalog for Rubin, and we won't have a shear catalog in a while because that's sort of more down the line production. So maybe we only get that in 1 to 2 years, but we want to sort of validate our PSF model before making the shear catalog. So that's why we're doing this kind of practice. Yes.
Yeah, so in Rubin observations, we will be calibrating PSF on each CCD with the approximately 20 stars that have high enough signal to noise ratio. And those are relatively bright stars compared to the extremely faint galaxies that we're trying to correct on. And so there is this issue that we heard of in the previous talk where there are corrections to the PSF that are bogus if you were just to use those stars, because there's more of a tendency for the charge to flow up and down parallel to the channel stops on the detector. And so with bright stars, the PSF becomes very elliptical. So we're planning on rotating the camera relative to north to try to average this down. But that's one of the fixes that we can introduce, but it's a big effect and it's an additive effect.
So I'm wondering, after rotation, that anisotropic line, you said vertical line, is it gonna be averaged into a size change of the PSF? Because if you
you got to go 180 degrees because it's a spin 2 field. So you go from -90 to +90, but you have to do it theoretically. You have to do it uniformly in order to cover it, but you can't do that because the seeing is always changing, and unfortunately, we're not allowed to rotate very often. That's a project level decision that's been made. So it's going to be very imperfect.
Okay.
And so we're going to end up, so we've been doing simulations in the laboratory on the CCDs that we're using in the LSST-Cam to see how well we can do.
What's the primary magnitude that this would happen?
So around 20th.
What effect are you thinking of, Tony?
The charge flows more easily due to charge spreading parallel to the.
So this is a bleed you're worried about?
Yeah, I mean, are you worried about wideband, possible wideband effect?
No. The PSF
Or just brighter
is
pattern or
not-
something else?
is not circular for a bright star.
But is it brighter, fatter, Tony, that you're worried about?
Yeah, effectively the anisotropic brighter fatter effect.
Right, so
So
I
that
mean,
creates,
if I can jump in, I think, right, we have a correction, which is good to a certain level,
right,
maybe not quite good enough. But I think the bigger issue is there are more stars than the number you cited.
there are definitely more stars and the signal to noise ratio is very low.
No, but I think that's not, I think that might be where there's a gap. There are lots of stars and.
On a co-added-
with
on a
sufficient
co-added
signal and
frame,
noise to
there are,
use.
yeah.
No, even on single images,
Instruments.
there are lots of stars. I think
Anyway,
there's a lot
we've
more
been
than
doing
that.
these simulations in the lab with a star field. And we can show you plots of
Sure.
residuals and they're pretty large.
Yeah, I would agree that it's important if this effect is there, we should test our model on fainter stars to see if there is a magnitude dependence on the PSF because most of the galaxies are faint. Is that
I mean, if I could add something, so the brighter fatter, you basically, after the correction, you have to throw out some of the brightest stars, and it's maybe 1 magnitude. In DESC, we did 1.2 magnitudes. Hopefully we'll do a little better in LSST. But you just throw them out, and then you test to see that if you have any residuals that are dependent on magnitude. It's an easy test, and then there's plenty of stars that are below the magnitude that are affected by brighter fatter. So we usually get like 100 to 150 per CCD in DES, which I think expected to be pretty similar in Rubin. So I'm not actually worried about that effect.
Yeah, MSIM images certainly show more than 100.
Thanks. Mike, do you know if this test is done on co-add image or
In DES, we do everything on single epic for the PSFs, and then for the coads, you coad all the single epic images of the PSFs to get the PSF of the coad.
And that's what Rubin does too.
Yeah.
Right.
so for baby step 2, assume we get the error budget for PSF schematics. We're thinking about how we should allocate those budget to different kinds of PSF correlation functions. So the fiducial choice normally is that we just divide the error budget because they add up quadratically. We divide them by 1 over square root of n, where n is the number of PSF correlation functions. But this sometimes causes an issue because some of the correlation function is well below the budget, so they're not using up the budget at all. And what ended up happening is one of the correlation function, for example, the leakage correlates with the size, that blew up the budget. And we're thinking about whether there's a better way to allocate the budget so that as long as the total systematic doesn't exceed, then we should claim that the PSF modeling is fine. I see your question.
Right, so pardon this question, is I do not do weak lensing work. I watch other people doing it from afar. But what I know about PSFs in other contexts, when you're asking structural questions, the scale in which you're asking that question is extremely important. That is, you may think, oh, well, the core is very vital, but it's not if you're in larger scales. Reciprocally, things on wide scales really don't influence the fine details. So the question is, if you ask what scales are the real signal of weak lensing coming from, what angular scales in the image, do you weight by that knowledge? Okay, because that's where your uncertainties are most important. Is there something like that in what you're doing? This is how the integral over the objects actually work, and this is where the portion of the PSF that we need to weight more than other portions.
Right. That's exactly right. And the scale we use for weak lensing is normally from about 5 arc-minute to, depending on how well the B mode is constrained, to 50 or to 200 arc-minute.
Mike
Oh.
has got a question.
Yeah.
No, I was just going to comment, but I think you're talking about there's two kinds of scales here, right? There's the size scale on the size of a single PSF versus the correlations between two different PSFs at two different locations. So what TQ answered was about the latter, but for the size of the image, the scale that's relevant is close to the full width half max. So our galaxies are not much bigger than a PSF, the ones that we usually use. So the parts of the image of the PSF image that we care about are really closer to the core than the outskirts. The Oriole stuff is not that relevant for cosmic shear. But no, my original comment though was going to be about your question about the 1 over root n. Usually there's only a couple of the correlations that are particularly relevant. So the beta squared rho 1 is a big one. In DS, we never had much leakage. So I think once we start switching to the more modern techniques of, anacal and metacal, they usually have alphas that are very close to 0. So hopefully that'll be true in Rubin. I'm relatively confident that'll be the case. And so it'll be the rho 1 is usually the dominant one. And so beta squared rho 1 is the term that is the most important.
Yeah, so I'm asking this because we're potentially want to include other terms. The thing about correlation function is if you include one term, you add n correlation functions because it correlates with everything else and itself. So first, we need to be careful of not adding too many terms. Secondly, thinking about more flexible budgeting here. That's the discussion I want this room to have. Let's move on. So here, this shows the current fiducial budget for one row statistics by divide the overall budget by 1 over square root of 6. So the baby step 3 is computing the prefactor of row statistics. So to provide a little bit of context here, how row statistic is converted to systematics on galaxy shear correlation is there is a prefactor that depends on the size of the PSF and the size of the galaxies in front of the row statistics. So we revisited this Pauli-Henriksen formalism on how how the PSF modeling error is converted to the galaxy shape error, and basically what you need to do is there are 4 terms here, including the leakage, which is written on the right side. You cross correlate and autocorrelate all of them to get your coefficient. I should mention that if you cross correlate galaxy shape with the PSF shape, it goes to 0. So there are 3 terms that are 0. And then we will end up having, so the cross correlation of EPSF delta T would be rho 3. There's term 2 and term 3 will be rho 4. 2, 4 would be rho 5. 3, 3 would be rho 1. And 3, 4 would be rho 2. And oops, I think I want to mention that in DS initial formalism, there's no effector 2 here. And we think that the cross correlation should really generate a 2 because you have you cross correlate. The extension would have 2 terms for the cross terms and 1 term for the auto correlation. So just want to get feedback from the crowd whether that's the appropriate way to get this prefactor. I'll pause a little bit for questions. I guess.
I
the-
mean,
the-
one thing here is that this is assuming a model, right? Or unweighted moments or something like that. So actually there's some pre-factors, right, that have to be calibrated off real data.
Yes. So this is the approach to compute that prefactor with the Gaussian approximation. And in the later slides, I'll talk about alternative way to get that factor. Like,
I could just add quickly, like so we originally had these like TPSF over TGAL factors, and it's a lot easier just to measure them empirically. And that's what we call beta and eta and these other terms. It's easier to just let the data tell you what those factors are, I find.
yeah, I think so. So in the actual analysis, we'll probably do that. But before we get a shear catalog, I think this is the only approach we can use to
Yeah,
test
they're
it.
order unity, so they're fine to just estimate something for forecasting.
Yeah, in a few minutes, you will see that using this approach and the empirical approach would generate very different requirements. And, I think so basically, if you do the practice of last slide, you would get this equation, which is slightly different from what we understood before. From the previous survey, we get a few numbers that tell us the average size of the PSF and the size of galaxy from HSC, DES, preliminary Y6, and possible DC2. And before showing the requirement, just want to explain the second approach that Mike mentioned. So in the actual survey, you can actually parameterize your prefactor in these alpha, beta, and eta term, and you basically cross-correlate your PSF shape with the galaxy shape to figure out what those terms are. And if you do it that way, the prefactor is just going to be the cross term and the auto terms for these. So row 1's prefactor will be beta squared, row 2 will be 2 alpha beta, so on and so forth. We also collected alpha beta eta term from the previous survey to compare their requirements set on Rubin. So yeah, so from now on, I'm going to show 5 slides to show that has the requirement of 5 row statistics. And as you can see now, the difference between the empirical fitting, so DS fit and HSC fit are using the empirical methods. The underscore PH08 is Pauling-Erickson formalism with the Gaussian approximation. So we can see that I think the DS fitting and the HSC fitting actually produce pretty different results in this case, or around an order of magnitude. The Pauling-Erickson also gets different results because of the average size of galaxy and shape are vastly different. So I guess the lesson here is that the requirement will depend a lot on the population of your PSF and galaxies. In general, if you have smaller galaxies, it's more sensitive to PSF uncertainty. And if you have larger PSF, it will also make it more sensitive. So here's the results for row 2. This is the most consistent between all 5 of the requirements. Row 3 is sort of a failure now, because you can see that the empirical methods give you very tight requirements within 10 to the minus 8. Also, can I reload this slide? Yeah. I put the row statistics on the side here. So row 3 is the size the PSF size error correlation. And the polyhedroxy is giving a very generous requirement. Before is kind of similar. Row 5 is also, so that all row 3, 4, and 5 are showing pretty different requirements getting from empirical methods and polyhedroxy. I suspect that it's the galaxy PSF size ratio you get from the fitting is different from your galaxy populations ratio. So.
Can I ask, so in the Paulin-Henriksen ones, are you taking mean galaxy divided by mean PSF as your coefficients for betas and etas and stuff?
I think so. So that's the trace of galaxy, trace of PSF divided by trace of galaxy.
Because that's different than the mean T-gal over T-PSF, all inside the mean.
Right. I think we did it separately. We took the mean of galaxy and mean of PSF and just take the ratio, not within the bracket. So yeah, it doesn't commute, but yes.
No, it doesn't. And that, I don't know if that's driving this difference or not, but I think those are different quantities.
Right.
So
Because you get
the trace of the
you get-
galaxy.
like you can see smaller galaxies when your PSFs are smaller. So they like that inside the bracket matters. Sorry, I cut something off. Apologies.
Oh, no, that's a good point. I was gonna say that the trace of the galaxy here is the pre-PSF. I hadn't thought of the selection effect. I think also the Paulin-Henriksen values are assuming a lot of things that aren't true, like unweighted moments and Gaussians, etc. So I think there's lots of reasons why it would be different.
Yeah, that's definitely true too, for sure.
Yeah, thanks for the suggestion. We'll definitely update the code so that it computes the ratio within inside the bracket. And so I just want to mention a few future steps we want to take on improving this model. So we want to use the covariance matrix to obtain the overall budget. You might want to consider higher moments. So in my previous work, I showed that for HSC, if you look at the force moment, which is sensitive to a slightly outer skirt of the PSF, you'll find additional additive bias to shear. So we want to test that for Rubin. We want to explore alternative ways to allocate the budget. So that's especially important if our budget is tiny and our PSF model exceeded that budget. And in that scenario, we might want to consider alternative way because Rubin is going to have very stringent requirement on everything for cosmology. So and the final step is quite clear that we want to compile this code into a QA or analysis tool so that it runs automatically with the PSF modeling over commissioning. So that's all I have. Final thoughts, questions, comments? Otherwise, that's it for me. Okay.
It's a question from Ruth.
Go ahead, Erin.
Yeah, I should also note that how it actually propagates to cosmic shear also depends on sum of few row statistics. I think it's row 1 plus row 3 plus 4 and 2 and 5 separately. So I think any requirements should still be on this combination of row statistics, not individually. And even when you include higher order moments, I anticipate there would be requirements on some combination of maybe second order and fourth order moments and something like that, and not on each and individual terms. And I think finding out that combination is probably more important, and that also means there'll be fewer terms to actually keep track of.
Right. Thanks for the comments. I think that's exactly what we're trying to do with finding these factors in front of the row statistics, because without the shear catalog, you really can't find it empirically. You have to sort of use a Gaussian approximation to find how they are combined, right? So that's why it's still pretty important in the early stage to figure out the prefactor in the Gaussian approximation. But yeah, you're right that 1, 3, 4 are combined in the same direction, and 2, 5 are in the other direction.
Thank you. Okay, so we talked kind of at the high level about the requirements on the PSF, and now I'm going to talk about actually testing how we're doing with the current implementation of Piff in the LSST pipelines. So as motivated already, we want to minimize additive bias to cosmic shear due to the PSF. And the PSF modeling packages which is currently implemented is Piff, the PSFs in the full field of view. So this was mostly written by Mike and implemented for DESC Y3, where it worked very well. And so now we're trying to understand if it will also perform well on LSST data, which among other things is, shorter exposures, different survey strategy, larger field of view, etc. And we've done these tests on simulated images. So we're generating these with MSIM, which is a DESC image simulation tool. So this is including like realistic models for the optics and the telescope from Batoid and weather patterns from PSF Weather Station. And we're using the OPSIM baseline survey strategy to select pointings for wide, fast, deep. And basically we're giving all of these things to MSIM, which generates CCD sized CCD images, which we then feed to Piff, which performs the PSF modeling. And we get out a PSF catalog that has PSF measurements as well as residuals for reserve stars. And the current configuration of Piff does the interpolation in pixel coordinates without including any color dependence. So we're gonna be still talking about row statistics. So I've labeled them on the side so you can sort of reference which ones mean what. And we can compare the amplitude of these row statistics with what Piff got for DSY3. I note that this isn't exactly an apples to apples comparison because there's different numbers of visits in the simulations. So DES has a larger number, which in principle should, the amplitude should scale as the square root of the number of exposures if you have independent realizations. But if that is true, then the square root of 16/29 gives you like a 3/4 factor. So it's not enough to explain the fact that simulated visits on the left have larger row stats than on the right. And if we just take a very hand wavy line, which was informed by the last talk for a requirement on row 1, we see that are exceeding it. And this is in G band. And we have the same problem of the number of visits scaling. So here, LSST Y1 is going to have twice as many visits as the simulations we have right now. And I did a test of whether this scaling of root n for independent visits holds for row stats. So here, each panel is the amplitude of one row statistic as a function of the number of visits that I am including in the catalog when calculating them. And I have used 3 spatial separation bins. So the different colors are like 1, 7, and 35 roughly arc minutes. And the lines are showing a root, 1/√n scaling from the first point on the plot. So just to give roughly an idea of what that would look like. And we see that at large separations, so the brown squares, we're kind of following this line roughly. But at the smaller separations, the amplitude is remaining much, much larger and not falling off as root n, which points to the fact that they're probably not independent. So we might have some persistent structure in those residuals. And I'm now going to just briefly touch on differential chromatic refraction because it'll be important for the rest of the talk. So this is a wavelength dependent effect on the point spread function. So if you have a source coming in from the left of this image, entering the atmosphere at an angle, it will be refracted, and that refraction angle depends on the wavelength of light. And so you end up having a smeared PSF, which will have different second moments from different second moments than if you were entering in the atmosphere at zenith. And this is very nonlinear with wavelength. So these colored lines are showing the relative refraction angles as a function of wavelength. And you see these are much, much steeper in, for example, the G band than RI and Z. And so wavelengths at one side of the band or the other will have a much larger difference in refraction angle than, for example, R, I, or Z. And we can see this in the simulated data. So this is a whisker plot showing the shape of the PSF at different locations on the field of view. And each line here is colored by the G-R color of the star. And so first of all, notice that these are very, very elliptical. This is at air mass 1.9. There's a little scale bar up here, ellipticity. And if you look at the residuals, so after the PSF modeling, hopefully you can see this on the screen, there's some interesting structure with color. So all of the blue stars are oriented sort of on one way, and then all the red stars are oriented at a 90-degree angle from this. And we can understand this. I will show a little drawing. So if you just have a PSF coming in at zenith, the blue stars will have a larger PSF than the red stars, and the gray is just sort of an intermediate color. With DCR, there will be a wavelength dependent smearing, so the blue gets stretched out more than the red. And when you run your PSF modeling, your PSF model will be sort of the average. And that means the residual, if you think about subtracting shapes is always hard, but basically the sign of the difference in E1 will be different on the blue and the red, which is why you end up with this degree rotation in the residuals. Yeah, so if you kind of just look at the red, you see that they stay aligned along the same direction.
Is there any mechanism that that gives you a clustered red cluster of stars, cluster of stars? Because in case if star distributed that way, you will get a correlation because if it's completely random, then the correlation should still be 0, right?
Across the full field.
Across,
Yeah, because this is a uniform effect. Yeah, I don't know.
Is that in your MSIM? Like, is the star catalog clustered in the MSIM?
I think they are randomly positioned. So in the simulations, there should be no spatial dependence, except for spurious.
In the real world, blue stars do tend to be closer together. Like they're the ones that are just born and haven't gotten time to spread out much yet. So they tend to be in open clusters and stuff. I don't know if that matters.
So we can quantify how much this DCR effect is impacting our residuals currently by just turning DCR off in the simulations and running our pipeline again. And so that's what is shown in the faint points. So you can see that for most of the correlations, turning off DCR decreased by 1 to multiple orders of magnitude the amplitude of the row statistics, except for row 1 over here, which has barely changed. So DCR is dominating most of the residuals, but there's still something funny going on with row 1. And some of us were sort of surprised when looking at some of these results because the DCR effect was a lot stronger than we expected. But a lot of that intuition comes from DES, which ends up having a very different distribution of air mass in their G-band pointings than LSST, at least as given by the current OPSIM simulations. So you can see DES ends at 1.4 basically, and we have this whole tail of large air mass pointings in G-band. And if you look at the difference in angle of reflection across each band as a function of air mass, DES ends around here at air mass 1.4, but for LSST, this high air mass tail goes all the way out to like 2.4, so we end up having like at least a factor of 2 stronger effect. And so this kind of poses 2 questions as whether the algorithms developed on DES will be sufficient, and should we be addressing this with algorithms, or should we sort of think about whether we should consider altering survey strategy or sort of making a metric for the survey cadence people that uses this information to inform the decisions. And can similarly look at these residuals in the I-band and compare with DES. This is DES RIZ combined. And this is much better overall. We don't see as strong of a DCR effect, but row 1 and row 2, especially at small separations, like roughly arc-minute scales, are still much, much larger, which we don't understand. And this is the rough row 1 requirement again. And one last thing is we also found interesting structure in stacked residuals on the focal plane. So this is size residuals from a couple of 100 visits. And on the corner CCDs, there's this radial wave pattern in the PSF residual size, which is probably due to vignetting. So this is basically showing the fraction of light that ends up on the sensors. And you can see that the corner CCDs that are losing a lot of light are the ones that have these strong residuals in the PSF. So we've done more tests than I showed here. So DCR was by far the strongest effect. We tried turning tree rings on and off, including galaxies, randomizing wind directions, and none of these things had much impact on our row statistics. And neither did the vignetting of the corner CCDs. If you don't include those, your row statistics don't really change. So one question for the room is what other tests we should add to this list. So always happy for input on that. And then some of these tests sort of gave us a lot of things to think about and work on. So we already knew DCR was going to be something we would need to address. So Piff also is going to integrate the color interpolation developed for DES into the LSST pipelines. But we have these questions of whether the linear interpolation is going to be sufficient. Yeah, should we be considering a survey strategy we've been testing Piff inside the LSST pipelines, but it's probably worth, doing the check of whether the same configuration of Piff standalone reproduces these results. The row 1 and row 2 have stronger signal that we don't really know how to explain. The vignetting detectors, so the PSF modeling for some reason is performing poorly there. And then there's been some question of whether the simulated DCR effect in GalSim is of correct magnitude or whether it's being overestimated.
I think the vignetting is probably bad flat fields in the simulations or something like that. I don't.
The wavefront goes to hell out there.
It does, but that doesn't look like that.
Yeah, I mean, that's a,
Well, we can look into it, but it's not the vignetting. The optics go to hell out there.
stop.
Well, actually, of the surviving rays that end up there, they don't make donuts, right? They look like a horseshoe.
I agree with all those things.
Yeah. You're ready for questions?
Yeah.
The issue with the row 1 and row 2 at those scales, it seems like the only thing that could really do it is the atmospheric modeling. There's too much power from the atmosphere coming in at those scales. So I wonder if you've tried on a smaller sample to turn off, really change the atmosphere model to remove the small scale power. Just to remove those angulars, the power from the atmosphere at those scales. It seems like it's gotta be.
There's a way of doing that. Is just in the simulation to increase the exposure time, to be closer from what DES was doing, because like in DES it was like 90-second exposure, where I guess here it's like 30.
Yeah, it's possible. Although on the other hand, DES is a smaller telescope, so there's if you just do the scaling from the atmosphere, it's you'd think it would be the square root of the time, but then some power of the diameter of the mirror, which goes the other way. So I'm not sure it's actually that different. But just in terms of testing, I wonder, have you tried really lowering the atmospheric variation to see? One thing to do is just really turn off the atmosphere and just make sure at a code level that you're getting, because then it should row 1 should go to 0 or close to 0. Just
Can
checking
I clarify your question, Erin?
Yeah, sure.
So I guess what you're saying is that you suspect that Piff is unable to model the PSF at high enough with high enough frequency variations. Is that the?
Yeah, maybe. It seems a little surprising, but to me that sounds like the most likely thing. You just have so it's quadratic spatial terms inside each CCD that you're using? Or cubic?
Yeah.
Okay. You would think that would be enough, but I think the only way to explain it is there's faster spatial variation coming in from the atmosphere, and the quadratic or cubic isn't enough to capture it. Oh, I guess the other question is, how many stars do you have? How many stars come through how many stars are you using per CCD?
What I remember is about 150.
Yeah,
Does that sound right? Does that sound right to you, Claire?
Sounds like that should be plenty. I think that would be plenty. Mike, you've got the floor.
Okay. Yeah, I had a couple of comments. So first, I think the high row 1 that you're seeing, my guess is that's likely due to those vignetted detectors that you showed on Slack that you didn't show here, I guess, but you mentioned number 4. I think they're probably dominating the row 1, so that's a algorithmic problem. We need to figure out how to model the PSF out there on those vignetted detectors. I don't know if it's sky diffraction or just some weirdness, but
I did the row stats without including those corner detectors, and they were basically the same.
Really? Oh, interesting. Okay, so that's probably wrong then. All right. Well, we still need to work on those, but that surprises me.
Actually, I'm sorry to interrupt. There's a question for DM whether we're actually going to use those, They're out, I mean,
Yeah.
there's some fiducial circle and those are outside the fiducial circle. I'm curious to know.
I
are we
think part
actually-
of part of the detectors are outside the circle, but part of them are in, I thought. I don't know. Anyway,
They're all outside.
okay.
We'll
But,
process, but we
They're all
use them.
outside 1.75. Yeah.
The code will run on them. We do it on HSC, which is even worse in the corners. We don't make much use of them, but we get it through.
Sorry.
Anyway, so my second comment was, so DCR is proportional to air mass squared minus 1. So just to give you a feel, people aren't used to thinking about that. Like, so in DS, that number goes out to 1. So 1.4 squared minus 1 is about 1. And if you go out to like 2.5 or so, like that's really big. That's like 5 or 6 times as much. So the upside though is that DCR is very easy to model, I think. So we don't explicitly do that in Piff, but I could definitely imagine a version, a model where we say, this is the direction to zenith, this is the, the air mass we're at, all this kind of stuff, and just include it in the model directly. I think that could be very effective. So I'm hopeful we can just do this algorithmically, right? It's not really there, and it's not even in the version that we did in DES for modeling the colors. But I suspect we can do a pretty good job modeling this.
Okay, thank you. Yes, question.
Yeah, I was thinking in terms of this question of survey strategy, there's a reason why those high air mass terms exist, and it's not us, right? It's the other science collaborations that need revisits of things. I suspect a better strategy, we might need to just say we won't use those exposures. We know what air mass that was observed, and it although there is some tail, it's not a gigantic tail. It may be better if we can't get a complete correction for things that are beyond air mass 2, just to not use those.
It is us, but it's not DESC.
Yes, yes, I stand corrected. Multiple hats.
Okay.
Yes.
I saw in the chat that the default is actually second order. Josh said.
Yeah, unless it's been overridden in the configuration you're using somewhere. But yeah, default is second order.
I didn't override that.
Okay.
So that's an obvious thing to test.
Yeah, try that. I bet that'll clean up the corners. Then but at some compute cost, right? So that's the trade-off.
That we were dominated by the simulation.
Okay.
Doesn't look like there's any more questions in the room. Does anyone else on Zoom or in the chat?
Well, I guess the point number 2 here is partly been addressed by our discussion because apparently they're not configured the same. I'm pretty sure, Mike, we use a third order in DS, right?
Not in Y6, not when we added the color terms. We did in Y3 though.
And that was because you'd have too many parameters.
Yeah, the
or
color
too
terms
many,
sucked up
right,
too
right.
much of the constraining power, so we couldn't get away with third order anymore. With the number of
Chip
stars
size
we wanted
is
to do.
different as well, right? I mean, they're 2K by 4K with 0.26 second pixels, and these are 4K by 4K.
I mean,
so
none of
There's
that is
similar
gonna
number of
give-
stars. So
none of that is going to give the size of the changes you're saying. I don't think any of those factors. Those also have. If it was 20%, maybe, but not what you're saying. There's something else.
yeah, in Y3, second and third order performed almost equally well. Like third order was only barely better.
But in terms of the actual, getting back again to what Erin said, I thought that the small scale correlation function was actually pretty good from the atmosphere in comparing to real data, like in the PSF weather station paper. Do I remember that right?
Sorry, what was the question?
Well, one of the things that Erin was worried about is maybe we have too much power on small scales. But I seem to remember that PSF weather station had been compared to real data. And it looked pretty good. Is that true?
So we didn't compare it at the level of correlation functions because we don't have data that is just the atmosphere to compare to it.
I think the other thing is that there's a difference in what spatial correlations are remaining after you do the time integration. That's the other that may be the other critical piece.
30 seconds. There's a lot of HSC 30-second integrations people don't usually look at. If we're interested in 30 seconds on an 8 meter, we could look at that.
Yeah, so thinking about what kind of comparison, there's all sorts of different data out there, but as you point out, getting something that you can really compare exactly, removing other effects is a little tricky. But yeah, I mean, I have some extracted results on spatial correlations for integrated results from donuts from DES. And those compare kind of at the 50% level with similar quantities that were done in atmospheric and ground layer seeing studies done for Rubin a long time ago. But those still have informed that informed the AOS work for a long time. And, you could probably extract something equivalent from the simulation if it's done right. And then that would, then there's a spatial correlation matrix on certain, whatever scale you choose that would be interesting to look at. That could be an apples and apples comparison. Okay. Right? And I think it would touch on exactly this issue. It's interesting. Yeah. Interesting.
Any other last comments or questions?
If you look at your shape residual in the field of view, make like full field of view.
Like this. So this is again just a couple hundred exposures. So it's a little bit smaller than the size.
Also that grid line, like what's the grid line? That the gap of CCDs?
Yeah, that's the CCD edges.
Yeah, seems like the edge, there's like correlation, like there might be correlation because of the edging. Other parts of the CCD looks pretty tiny, like the size ratio looks tiny.
Yeah, you could trivially cut out the rims, the picture frame of each CCD and see if that makes a difference. I mean, that would contribute to a bunch of scales. So it's a good suggestion. I mean, yeah, is there any, yeah.
I'm just curious, does the simulated PSF have the extended wing mentioned in the?
No, 5 oxygen.
Sorry, I couldn't hear that question. Can you repeat it?
Does the simulated PSF here has a very extended wing, like to 5 arc-minute, like what's mentioned in crystal? I think you need to repeat.
The question is whether the simulated PSF has extended wings.
No.
We just get out what a batoid produces, which it won't have, as far as I know, it won't have all the effects.
Yeah, probably only goes out 50 pixels or, at most for most.
Something like that, yeah.
Yeah.
Okay, cool. Thanks everyone for the discussion.
Thanks, Fred. Yeah.
Good to see everybody.
Yeah, thanks,
We're closing the
Mike,
session.
Josh, Erin.
Thanks everyone.
Somebody was